Parameterized algorithms, once again, so the motivation for doing this problem or for the area of parameterized algorithms is NP completeness. Okay. So NP completeness, we already know that if a problem is NP complete, the implication is that unless P equal to NP, you cannot find an algorithm, you cannot design an algorithm. So if a problem, let's say pi is NP complete, the implication is that unless P equal to NP, you cannot design an algorithm. It's not expected that an algorithm that solves the general instance of pi exactly in polynomial time is possible. You don't expect such a algorithm, right? Now you can see that there are three terms there. Says, okay, you cannot solve a general instance exactly in polynomial time. Okay, so all these three are important for an NP complete problem. In that, if we reduce, if we ignore one of these terms, it is possible that we get a good algorithm, right? Like for example, you take the vertex cover problem. So vertex cover problem, it is NP complete in general graphs, right? But let's ignore about this general instance thing. Okay, so it's not a general graph. We are looking at special graph classes, right? Then we know that vertex cover can be solved exactly in polynomial time in special graphs like trees, bipartite graphs, etc. Right? And similarly, suppose we ignore the exactly part. Okay, so we want to solve general instances in polynomial time, but not exactly. And this is what you saw yesterday. You can find approximation algorithms that runs in polynomial time for every instance of vertex cover problem, right? Okay, so now the third one is, okay, what if I want to solve every problem, every instance, that is, I want to solve a general instance exactly. And it's an NP complete problem. So I know that unless P equal to NP, I have to spend exponential time. Right. So this is what we saw yesterday also. Right? So I know that I have to spend exponential time. So yesterday we discussed how to, okay, what if you have to spend exponential time? How can we improve that exponential time? That was exact exponential algorithm, right? So today in parameterized algorithm, we'll do something a little bit more smartly. Like, okay, so we know that we are going to solve this general instance exactly. And we know that we have to spend exponential time, right? Okay, now every problem instance, it's represented you can you represent that using a size, right? So every problem instance, whether it is, okay, for example, if it is a vertex cover, it comes with a graph G, right? And you can assume that the size of this input instance is n, right? And you express the running time as a function of n. Okay, now this running time function for a NP complete problem, we have to expect it to be exponential. And yesterday what we discussed algorithm where it is exponential in n, right? But if you think about it, n is something that is supposed to be grow very large, right? So we want, the purpose of designing efficient algorithms is to design or is to solve the problem for arbitrarily large values of n, or n is something that you expect to grow, right? So an exponential in n function, as n grows, becomes less and less efficient, right? Okay, so the idea of parameterized algorithm is, in addition to n, the input size, you add something to the problem. Okay, so you have for this you have G, okay, and you which is of size n. You add something else to the input, okay. That we'll call as a parameter, and we represent it as using K. Okay, right. So a parameterized problem, it contains a parameter in addition to the input. There is an input and there is a parameter also. So you have input and a parameter. Okay, and the idea is, or the motivation for doing this is, okay, we are assuming that the parameter is much lesser than K. Okay, right. So parameter is something which is much lesser than, or this is your assumption basically, right? Okay, and the running time, which is going to be exponential, okay, you make it exponential only in K, but polynomial in N. And that's what a parameterized algorithm is. So you solve the problem exactly for a general instance, but your running time is something like this. Your running time of the algorithm is f of K, and in N it is only a polynomial time. So it's like n power C for the constants. Okay, and is the parameter going to be much lesser than n? Yes, that is the assumption. Okay, there may be instances where the parameter is very large, but for such instances, parameterized algorithm doesn't hold much value. Okay, so what you say is, okay, so you look at this running time. This running time is very efficient when K is much smaller than n. That is ideal. Okay, so what are you trying to do is you're trying to contain that polynomial, the exponential expansion of the running time into a measure which is something smaller. See, when K is a constant, you can even think of K as a constant. When K is a constant, this is even a polynomial time algorithm, right? When K is a constant, f of K is also a constant. So we'll see example. So before the example, I'll give you the formal definition. Okay. So a parameterized problem, usually when you say a problem, it's just an alphabet. Here you have an alphabet and an integer, which represents the value of the parameter, and and which is called the parameter. And for a parameterized problem, you say that there exists an algorithm which we call as a fixed parameter algorithm or an FPT algorithm, fixed parameter tractable algorithm. If the problem can be solved in f of K, then the input size and a polynomial function in input size. Okay, so this is the running time that you are expecting. Okay. Yeah. So is the definition clear? We'll see an example. I hope it will be better when we see the example. Okay. So I hope all of you got it. Now, okay. Now again, there is a difference, one more difference from what we saw yesterday. So yesterday yesterday our exponential function was in terms of n. Today its exponential function is in terms of K, the parameter. That is one thing. The other thing is, it is possible that for a given problem, when I say problem, or for a given parameterized problem, that means you have a problem and a parameter also. An FPT algorithm might not exist also. It's not given that for every parameterized problem, you can design an algorithm of this running time, f of K, xk, poly in xk. This might not exist also. Okay, like just like you say, okay, there are problems for which polynomial time algorithms most probably do not exist. There are parameterized algorithms for which parameterized FPT algorithms most probably don't exist. Okay, so that you have to keep in mind. We are not going to explore the interactability part in the course in the talk today, but that's something that you should understand. Okay, so we'll see. Okay, now you will ask, okay, I've been saying parameter, add a parameter. What can be a parameter? So the most common parameter, what we call as the standard parameter that you can add to a parameterized problem, is the output size or size of the solution. Like for example, you take the vertex cover problem, right? So vertex cover problem, you are given an undirected graph, okay? And your question is, does there exist a vertex cover of size at most k? See, this question is slightly different from the questions that you discussed yesterday. Yesterday in the approximation algorithm talk, you probably asked the question, find the minimum cardinality vertex cover. Okay, that was an optimization question. This is a decision version of the question. Actually, you can see that both questions are equivalent. If you solve one, you solve the other also. Right. So I'm going to ask this question, does there exist a vertex cover of size at most k? Okay, in a standard parameterization of vertex cover, your parameter will be k. That is the size of the vertex cover that you are looking for. Okay, and can I expect k to be small? I mean, there are instances where it is reasonable to see that, okay, you're looking for a small sized vertex cover compared to the actual size of the graph. Right. And again, parameter can also be any structural parameter of the input. For example, if it is a graph problem, it can be max degree, tree width, etc. For satisfiability problems, number of clauses that needs to be satisfied, etc. Or geometric problems, dimension, number of points, also any other. Okay. Okay. So any questions so far? Okay, one more point is parameterization. You can also consider a combination of parameters. So you can think of vertex cover parameterized by two values. Okay, but so vertex cover parameterized by solution size plus the tree width of the graph. Okay, right. Okay, is it? It's not a greedy approach. So it's like, I will think of it as you're trying to understand the problem a little bit more deeply, right? So what is making a problem hard, right? Is it the presence of this quantity or another quantity? And it's not at all artificial. I mean, practically also you can see a lot of applications. Like for example, if you take graphs or you take like real life graphs, like your road networks or communication networks. So there may be actually all these networks or graphs. There are some structural parameters which are always small in this, right? So instead of you try to come up with a 2 power n algorithm or 3 power n algorithm, you can make it a 3 power k n square algorithm. The running time will be better if k is small. So yeah, so finding that parameter also, that's why I call it art of parameterization. I mean, you need that you need that intuition to look at, okay, what is the right parameter to look at. So if you try to color using k colors, first k can be considered a parameter there, but then it is not solvable. It is not solvable in FPT time. Yeah, that's a good question. Right? So if you consider graph coloring problem where the number of colors needed to color the graph as a parameter, then it does not admit FPT algorithms. You can think about it. It's not very difficult because we know that when k equal to 3 also it's an NP complete problem. So I'll let you think about it. If you still have a doubt, I'll explain it at the end of the class. Any other? Okay, right. Yeah, so again, it's not only the problem, it's a combination of problem plus parameter, right? Like you take the graph coloring itself. So if you take graph coloring and the number of colors as a parameter, then there is no FPT algorithm for it. Okay, but if you take a graph coloring instance with like see the size of the vertex cover of the graph as a parameter, then it admits a FPT algorithm. Okay, so you cannot, in general, you cannot say, okay, this problem is admits an FPT algorithm, and this does not. You have to take a combination of the problem plus the parameter. For another example, the dominating set problem. So dominating set problem, the standard parameter, it does not admit FPT algorithm. But if you consider for example, what max degree, the maximum degree of the graph as a parameter, then it admits an FPT algorithm. Okay. Okay. Right. So in this talk, we'll see some basic techniques for designing FPT algorithm. Again, it's just the tip of the iceberg. I'm just giving very basic techniques. Okay. So the first one is bounded search trees. This is similar to the branching algorithms, actually the branching algorithm that we saw yesterday for exponential time algorithms. So here again, we start with a particular part of the input, then you branch on a bounded number of options. Okay, but here the search tree, the size of the tree, okay, it is bounded by a function of the parameter. So yesterday we saw independent set problem and we branched on it and we bounded the tree as a function of n. If you are trying it for a parameter k, that size of the tree, you should be able to bound it by a function of the parameter. Okay, so let's go right ahead and see an example. So the vertex cover problem. So I take this again. Okay, so does there exist? So you're given a graph with n vertices, let's say, and the question is, does there exist a vertex cover of size at most k? The parameter is k, right? So, okay, how will you solve it? So forget about the parameter. Just say that, okay, just imagine the question is there a vertex cover of size at most 10? Okay. Can we solve this problem efficiently? So I'm asking, instead of taking a parameter, I'm giving you a constant. Right? So you have to check whether there exists a vertex cover of size 10 for the given graph with n vertices. How will we solve this problem? Is the problem NP complete? It is polynomial, right? So you can look at all possible subsets of size at most 10 and check, then do brute force on these sets, right? So then you can solve when it in n power 10 time. Actually, even you take n power, this can be solved in n power k time, but this is not an FPT type. Okay, see, why? Because in FPT running time, you need this function involving k and function involving n to be separate. See, this was the running time that you are looking for in FPT. So this is FPT. Okay, so this brute force, the EC brute force algorithm, it's not an FPT algorithm. Okay, and the reason why you are looking for such a running time is, this somehow lets you lets k also grow a little bit, but not very large. So like, for example, if you take n equal to some 1000 and k equal to some 10, you can just compare this running time. You can see that this is more efficient. Okay, right. Okay, So your question, coming back to the question, so how do we design an algorithm using a branching technique? So to recall, in a branching, what we started with some part, and we decided, okay, or we enumerated there are only like a bounded number of um, options from here for the solution, and we branched on that options. So how can we do this for a vertex cover? Where should we start? So I will start with this knowledge, right? So I know that you take an edge in the graph. You take take an edge in the graph. So in a vertex cover, you have to solve, you have to cover every edge, right? By definition, if UV is an edge, either U or V or both should be in the solution, right? Okay, so you know that vertex cover should contain U or vertex cover should contain V, right? And you branch on it. Okay, so you say you start with an arbitrary edge EUV, okay, and your question is what? You're given a graph G and you're asking the question, does there exist a vertex cover of size K? This is your question, right? Now in one branch, you will take U, okay, add U to vertex cover. In the other branch, you add V to the vertex cover, add V to vertex cover. Okay, you know, though at least one of them should happen, right? Okay. Okay, so what should be the sub problems that you are solving in this here? Once you add a vertex to the, so let's say UV, okay, once you add this vertex to the vertex cover, what can you do? So so this edge is covered, all the edges which are adjacent to U is covered also. So you can forget about it, right? So here you have to solve the rest of the problem, that is G minus U. Okay, so you can delete U from the vertex cover instance, but you have added you are added U to the solution, right? So now you are asking the question whether there exists a vertex cover of size K minus 1 for this graph G minus U. Okay. Similarly, on the other side, you'll take G, you delete V, and you ask K minus 1. And you repeat on this, both sides. You can recurse actually. That is the, so yeah, so for every edge, you take either U or V and branch on which endpoint is added to the vertex cover solution. Right. Is the correctness clear? You can say yes if it is. Then, okay, what will be the running time of this algorithm? So what is the work done here? You are adding U to the vertex cover. You are deleting U from it, and you are reducing the budget. That can be done in polynomial time. Okay, so basically you will get a, so there are other two things, right? So at every point, what you can do, so let's say that some point G minus U becomes empty. Then what will you do? So when you're keeping on recursing, but fine, when you delete a vertex, let's say that you get a graph with no edges at all. So what can we do there? We can directly say yes, right? Yeah, we return true, right? So when we, okay, and what happens when this value, the parameter becomes 0? Cake, I mean, you are keeping on reducing, right? So the parameter can become 0 at some point. Then you return false, right? So then you are asking the question, okay, can you Okay, does there exist a vertex cover of 0 vertices? So unless, if the graph has at least one edge, then it is a false instance, right? So that's how you will, like if you have to implement it. So let's say you are given a graph, we see G comma K, this is the question. So what you can check is, okay, if G is empty, you return yes. Else, if K is 0, you return no. Okay. Else, you return one of this. So you return VC. Okay, let's say that E is EUV is an edge. Okay, so you repeat VC G minus U K minus 1 or logical or VC of G minus V K minus 1. This is your algorithm. Okay. Right. So what is the running time of this algorithm? You can represent it as a tree, right? So you start with G comma K, then you have at most 2 child nodes where you go from G minus U K minus 1 and G minus V K minus 1. And even here you have at most 2 child node, and here also you have to at most 2 child node. And the work done in every branch, every node is polynomial. You're only deleting an edge and looking at its neighbors and etc. etc. Okay. And what can be the height of this tree? So the running time will depend on how many nodes are there. You're doing a polynomial time of amount of work in every node. Log k, no, it is not log k. Height of the tree. See, when you go to a child node, you are reducing the budget, right? And you stop when k becomes 0, right? So the height is k. So you have a binary tree where the height is k. So the number of nodes in this tree is what? Order of 2 power k, right? Okay, yeah. So that is the running time of the algorithm also, right? So yeah, so the running time of the algorithm is 2 power k, then some polynomial factors. We are ignoring the polynomial factor for now. So this is okay. So we know what we have shown is vertex cover parameterized by the solution size admits an FPT algorithm with running time 2 power k. Okay. Is there a question? Okay. Okay. Right. Now, as always, you are also interested in, okay, now you get a algorithm of 2 power k running time. Can I do better, right? Can I get a better running time algorithm? And when I say better here, what I mean is, can I improve this function 2 power k to something smaller, right? And in fact, it's easy to do that. Okay, so you look at another branching option. Okay, so earlier we took an edge and we branched on which endpoint to take into the solution. Now, instead of this, you start with a vertex. You know that there are 2 possibilities with that vertex. Either you add that vertex to the vertex cover. Okay, so that is one branch. So you start with a vertex V and you say, okay, in this branch, I will add V to the vertex cover. What happens when I'm not adding V to the vertex cover? Right? So there is this vertex V. If I'm not adding V to the solution, all the edges that are adjacent to V should be covered, right? And I have decided I'm not taking V. in this branch. So that means I have to take all the neighbors of V to the solution, right? So if I'm adding V on one branch, on the other branch I'm not adding V, that means I am adding all the neighbors of V. Okay, all right. So okay, so here you had your budget K. Okay, here you have budget K minus 1. On this side, your budget drops by budget, I mean the value of the parameter, the size of the solution. It drops by the size of neighborhood of V, or the number of neighbors of V. So this is my new algorithm, new branching algorithm. So at every point I'll start with a vertex, and I will branch on whether I add that vertex in the solution or I add all its neighbors to the solution. What if some of the neighbors have an edge in the first one? In which branch? So it's okay. If I'm adding something to the vertex cover, you already cover all the neighbors, all the edges of the neighbors, right? So suppose I'm taking V. When I'm taking V, all these edges are taken care of. When I'm taking, let's say, all these neighbors, these edges are taken care of. Also, there may be other edges. I mean, there can be edges between them also. Right? They are also taken care of. Okay, right. The same thing. So when you're adding a vertex to the vertex cover solution, you in the child node you can delete that vertex. When you're deleting a vertex, you delete the name edges also. You can forget about it. Okay, right. Okay, so this is my new algorithm. It looks like, okay, I might have reduced the size of the tree a little bit, because on one side it is dropping by 1, but other side it is possibly dropping by more than 1. How can I say it drops by? Surely drops by something. Like it is possible that V is of degree 1, in which case this is also K minus 1. So we can say something similar to what we did yesterday for the independent set problem. So we can assume that you can assume that there exists a vertex of degree at least 3, right? Otherwise, if every vertex is of degree 2 or less, then what is the graph is a path or a cycle, and you know how to find the vertex cover of a path of a cycle in a polynomial time. Okay, so therefore you can assume that the maximum degree is at least 3, and in the branching algorithm you can always pick a vertex whose degree is at least 3. That means in the search tree, on one side it is dropping by 1, on the other side it is dropping by at least 3. Okay, so that gives you this recurrence for the running time, which will be 1.446. So this is, we have improved from 2 power k to 1.4656 to the power k. Okay. Yeah, so I hope it's clear. If there are any questions, please ask. Okay. Then we'll move to the next problem, the feedback vertex set problem. Okay. In the feedback vertex set problem, you're given a graph and you're, okay, what is a feedback vertex set? Feedback vertex set is a set of vertices such that every cycle contains one of that vertices. Like what was vertex cover? Vertex cover is a set of subset of vertices such that every edge contains one of those vertices. And in feedback vertex set, it's a subset of vertices such that every cycle contains one of that vertex. In other words, if you delete a feedback vertex set from a graph, the graph becomes acyclic. Okay. Like for example, yeah. So for example, if you say take this graph, what will be a feedback vertex set for this graph? If I take, I don't know, if I take, I think D and A, it is a feedback vertex set, right? Yeah, this is a feedback vertex. I don't know. I think that's also the minimum feedback vertex set. Okay, right. So, okay. So the question is to find a minimum feedback vertex set, or equivalently here the question is, does there exist a feedback vertex set of size at most k? This is a polynomial time, this is an NP complete problem and you don't expect a polynomial time algorithm. So we'll try to give a FPT algorithm where the parameter is k. Okay, right. And we are trying to give a bounded search tree. Okay, fine. So here we'll do some pre-processing. We are with the instance. We'll call it the reduction rules. We apply some reduction rules. So, okay, so here we are not assuming the graph is simple or anything. So the graph can contain self loop or multiple parallel edges and all. Okay, and we do some reduction rules with it. Suppose a graph has a loop, right? So if there is a vertex which has a self edge, okay, right? So, and this is a cycle, right? A loop is a cycle, right? You have to choose one vertex from every cycle in a feedback vertex set, and there is only one way to do it. Okay, if there is a loop at A, you have to add A to the feedback vertex set. There is no other way. And that is your first reduction rule. Right? So if there exists a loop at vertex V, then you add V to the solution. Or equivalently, you delete V from the graph and decrease the budget by 1. Okay, so that's the first pre-processing step. And the second pre-processing, if there is an edge of multiplicity greater than 2, what do I mean by that? So like, let's say there is UV and let's say there are many parallel edges between U and V. Okay, and these all form like a number of cycles, right? And you have to choose some vertex from this. So what in your pre-processing step, what you're doing is, if it is more than 2 parallel edges, you delete all the parallel edges except 2. Because you hit, or you say you select a vertex from this cycle, you select a vertex from all the other cycles formed by the deleted edges. So that is your second reduction rule. Okay. And third one, if there exists a vertex of degree at most 1, right? If so vertex is, if the degree of a vertex is 1, then it is not part of any cycle, right? It's not part of any cycle. So you can safely, you know that that vertex is not going to be part of any feedback vertex set. So you can just delete that. Okay. And there is one more reduction rule. The first step is that if there is a vertex of degree 2, what happens then? Okay, suppose you have a vertex of degree 2. Okay. So just give me a yes or no. So let's say V, U, W, and the rest of the graph. Okay. Can V be part of a feedback vertex set? Let's say yes. What do you think? Is it possible that V is part of a feedback vertex set? Okay, I think there is a question. Okay, so he's asking about how the decision version becomes equivalent to the optimization version. Actually, that works for the feedback vertex set also. Yes. So in fact, one direction is clear, right? So if you solve the optimization version, you solve the decision version also, right? If you have an algorithm to find the minimum vertex cover, you can answer the question, does there exist a vertex cover of size at most k? To find the minimum and see whether it is greater or smaller than k, right? Okay. And in the other direction also, you can keep, you can take different values of k, right? And that is like, how many values are there for k? Can be a polynomial, as it can be at most n values of k. Actually, you can do like something like a binary search and bound it by log n. Okay, so that there is a difference, but it's only like a log. It's only by a factor of a polynomial function. That's why it doesn't matter. Actually, you can make it only logarithmic factor. So it's very small. Okay. So coming back to this question, U and W connected here. Oh, it depends. It may or may not be connected. Okay, let's say U and W are connected. They are adjacent. Right. Yes. Yes. So that is it, right? So it is possible that U is part of feedback vertex set. But the idea here is, since V is of degree 2, U and W are its neighbors. Any cycle V is part of, U and W are also part of it. Right? So why do you have to choose V? Or instead of choosing V, you can choose U and W. Okay? Right. So therefore, your reduction rule is, if a vertex is of degree 2, you delete that vertex, you delete V, and you add an edge between its neighbors. Okay, if an edge already exists like this, then you add a parallel edge. Okay, right. So this is your third reduction rule. So if there is a vertex of degree 2, then you can delete and connect its two neighbors by a new edge. And it is, I hope it's clear that this is safe to do, because if you have a vertex cover of V, you can replace it with a vertex cover of which contains U or W or both. Okay. Okay. Yep. So you repeatedly do all these reduction rules, all these pre-processing step, and once you finish doing it, your graph has these properties. You get a graph which contains no loops and which has only single and double edges. The multiplicity cannot be larger than 2. And the minimum degree is at least 3, because degree 1 vertices you have deleted, degree 2 vertices also you have deleted. Okay. So we have a graph with more structure. Now, why are we doing this? Because once we have all these ready, we can use a property that if we are in a graph with minimum degree 3, okay, then suppose G is a graph with a minimum degree 3. Okay, let's take vertices and order them by their degree, so that V1 is the maximum degree vertex, V2 is the second maximum degree, or okay. So it's a, okay, I won't say rather than descending, I'll say it's a non-increasing order of degree. Okay, so we take these vertices and order them by their degree. Then we can prove this property that in a graph of minimum degree 3, the feedback vertex set contain at least one vertex from the a feedback vertex set of size k. It contains, if it exists, it contains at least one vertex from the first 3k vertices. Okay, that is by first I mean the vertices of highest degree. So if I take V1, it's the highest degree vertex, V2 is the next highest degree. Similarly, if I take all these vertices till the 3kth largest degree, one of these vertices should be part of feedback vertex set. It is not a very difficult proof. I mean, you just have to think of what the properties of feedback vertex set are. But anyway, we are not proving this in the class, in this talk, but we can just take it as a black box, right? So this is the theorem that we are, this is the result that we are going to get. So every feedback vertex set of size k contain at least one vertex of size from the first highest 3k degree vertices. Okay. So if this lemma is true, or taking this lemma as a black box, can we design a branching algorithm? We know that. No? Now what do we know? If you take the highest degree vertices and the first 3k vertices, at least one of them is in the solution that we are looking for. We don't know which one, but we know one of them. But the good thing is this option is bounded by a function of k now. We have like 3k vertices and we have to choose one. And we will branch on it. Okay, so that's our branching algorithm. So you take vertices by highest degree and you branch on the first 3k vertices, v1, v2 up to v3k. And in each branch you take, so in this branch you take v1 into the solution, you delete v1 and solve the rest of the problem using a parameter of k minus 1. And similarly for everything. And this algorithm runs in 3k to the power k time plus some polynomial running time, which we are ignoring, right? So we have a tree whose the degree of every node is at most 3k and the height is again k, because when you go from a node to its child node, your budget decreases by 1, it goes from k to k minus 1 and so on, right? So the height of the tree is bounded by k, it's at most k. The degree is at most 3k. So the total number of nodes in the graph is at most 3k to the power k. So this is a running time of k power k and some polynomial running time. So feedback vertex cover, feedback vertex set parameterized by the solution size also admits an FPT algorithm of running time k power k and poly n. In fact, you can improve this running time to something like 3 power k and all using other techniques. But this is the branching algorithm. Okay. So, I mean, this will be a good point to ask questions if there are any, because I'm moving to the next technique. Connected. Not only cycles, you delete that vertex. When you choose something in the feedback vertex set, all the cycles containing that vertex has the property that one of the vertices is in the feedback vertex set. So you just delete that, and so clearly all the cycles will go away, will be deleted, and then you continue. Yes, you make, okay, so you have a new graph, and yes, but again, you have a new graph, you have to find in that graph what is the largest 3k degree vertices, but that can be, again, you can do it in polynomial time. Yeah. So in the tree and every node you are doing some work, but that is bounded by a polynomial function, and the size of the tree is 3k power k. Okay. Yep. Okay. So we'll move to the next technique in designing FPT algorithms. No, actually, so this is kernelization. Kernelization is it's some process which is interesting outside the parameterization also. Because here what we are doing is, in kernelization, the idea is simple. So you pre-process, you do some pre-processing step on the input. So you start with your problem, let's say g comma k, okay, and you pre-process, you add some steps here. Okay. And moreover, for this pre-process, you only use polynomial time. Okay. So after the pre-processing, you get a new instance, let's call it G prime, and your parameter also might have changed, right? K prime. Okay. And if, okay, and if this is a kernelization, okay, then you can say that what do you need is that the size of G prime, the reduced instance. So here the size of G is n, right? Okay, after this pre-processing, you have a reduced instance whose size is bounded by a function of the parameter. Okay, it is independent of n now. And the new parameter is also a function of, it's also bounded by a function of k. So basically you get a new instance, and moreover you need this instance to be equivalent. That means, what do you mean? What do you mean by gk is equivalent to g prime k prime? That is, gk is true if and only if g prime k prime is true. That's the definition of equivalence. Okay, so you get an equivalent instance whose size depends only on the parameter k, combined size. It is independent of it. Okay. Now this is good. Why is this interesting? Because once you get a reduced equivalent instance whose size depends only on k, even if you do solve this g prime k prime using brute force, you will only spend time which is which depends only on the parameter k. See, the size of g prime is independent of n. So whatever algorithm you use on g prime, it's not going to depend on n. The running time is not going to depend on n. The running time will only depend on k. So even if you do brute force on g prime k prime, it will take only exponential in k time. And the time you spent on or the running time where it depends on n is polynomial time taken for pre-processing. So if there exists a kernel or if there exists, so this polynomial time pre-processing we call as a kernelization algorithm, right? So, or if a kernelization algorithm exists, we say kernel exists, or we call that, okay, this reduced instance g prime k prime, we call this as a kernel of size f of k. Okay. Now, if a kernel exists for a problem, okay, if you take a parameterized, for a parameterized problem, you can always pre-process it so to a reduced instance, an equivalent reduced instance whose values whose size is independent of n and it depends only on the parameter. Okay, then you can say that an FPT algorithm also exists, because what you can do, you can take a polynomial time algorithm, reduce it to get a kernel and solve kernel in any way you need, but that running time is going to be bounded by a function of k only. So that is an FPT running time. Reduction, yes. So what we did, reductions can be similar to the reduction rule we followed in the feedback vertex. Yes, it will be something. So that was also a reduction rule, right? So we started with an instance, we deleted vertices of okay, what is a reduction, like self loop, and we reduced. So we got an equivalent instance there. Okay. Okay. So in kernelization, rather than the actual running time of the algorithm, what we are trying to optimize is this the size of the kernel. That is also an independent. I mean, that's also an interesting, or that's what we are going to discuss now. Right? How can we get a kernel of size? This is the optimum size. See, this f can be an exponential. Even if you get an exponent time, I mean 2 power k kernel, it is fine. It's still FPT. Yeah. So kernelization is okay. There are other more interesting things about kernelization. it's different from other techniques, design techniques in FPT, in that kernelization is somehow kind of equivalent to fixed parameter tractability. Okay, so like for example, you say that okay, there is this problem. We know that it is FPT, but it does not mean that okay, it admits a branching algorithm, right? Or if you see another technique like iterated compression, it does not mean that okay, it admits an algorithm of that type. But for kernel, you can always see that okay, if a problem is FPT, it always admits a kernelization algorithm. Okay, and we have also seen that okay, if it admits a kernelization algorithm, then it is FPT. So in this sense, this is equivalent. So a problem is FPT. It is equivalent to say that it admits a kernel. All right, there exists a kernelization algorithm. That way, it is different from why this is. I mean, okay, I will. I mean, it's not very difficult to see. Maybe I'll give you references if you are interested. Okay. Okay. So this is what we are going to do. We start with a parameterized problem. We reduce it in polynomial time using a number of reduction rules so that you get a new instance which is whose size is independent of n. That is a kernelization. So this is the formal definition of kernelization. So let's see some examples for kernelization. We'll start with our favorite problem, the vertex cover problem. Okay, the question is clear. Okay, so you're given a graph G, let's call it VE. And the question is, does there exist a vertex cover of size K? And the parameter is K size, right? Okay, so we will give some reduction rules now. So the first one is if G contains an isolated vertex is a vertex of degree 0, then you can delete V from G. I mean, it's easy to see why this reduction rule is okay to use, because if a vertex is of degree 0, it's not going to be part of a vertex cover, right? So that's, and the second reduction rule will be, okay, so this is, I think this is a very, yeah, these are the only two reduction rules at it. So the first reduction rule, we looked at vertices of degree 0. Now, what if a vertex has very large degree? Now, what do I mean by very large? It has degree at least k plus 1. Okay, so k is our parameter. So there is a vertex V with such that degree of V is greater than, strictly greater than k. Now, what can we say about this input, this vertex? Okay, I think there was a question, would kernelization is always possible? Yes, so that's what I said. So if a parameterized problem admits an FPT algorithm, or if it is fixed parameter tractable, then you can say that okay, it always admits a kernelization algorithm also. Okay. Okay, so let's get back to this problem, the vertex cover. So what happens if there exists a vertex of degree, let's say k plus 1? We are looking for a vertex cover of size k, at most k, right? Okay, so is it possible that, okay, suppose there exists a vertex cover of size k, is it possible that this vertex V is not in that vertex cover? Or what happens? Okay, so let's say that, or you take any vertex cover. Okay, suppose there is a vertex cover which does not contain V. So how can we cover all these vertices? There is only one way to cover all these vertices, right? You have to take all the neighbors of V. But how many neighbors are there? The degree is greater than k, so there is at least k plus 1 neighbors, right? So yes. So the vertex V should be part of any vertex cover of size K. Okay, we don't know whether a vertex cover of size K exists or not, but if exists, then V should be part of it, that we know, right? So if a vertex of degree K plus, at least K plus 1 is present in the graph, then we use this reduction rule, that is, if there is, we are taking it to the solution. So, or equivalently, we say we delete the vertex and its incident edges, and also we decrease the parameter by K. Right. Okay. So it is clear, right, that these two reduction rules are okay, and what we get after applying this reduction rule is an equivalent instance. Right? So what did I do? I did, like, I started with a graph and just a parameter K, and maybe I used like a reduction rule 1 and reduction rule 2 as much as possible, as long as it is possible to use these reduction rules. And finally, I get this new graph G prime, K prime, right? Now, what do I know? So yeah, new graph G prime and the parameter, let's say it's K prime. Okay, I'll just call it K itself. Okay. Okay. So what can I say about G prime now? See, G prime is a graph where I cannot use reduction rule 1 or reduction rule 2, right? So what can I say about G prime? I know that the minimum degree is at least 1. There are no degree 0 vertices. If there is a degree 0 1 vertex, I would have used reduction rule 1, right? Then I also use reduction rule. Okay. Also, I know that there are no high degree vertices in the graph. What is the maximum degree of the vertex of any vertex in G prime? It should be K, right? Because if there exists a vertex of degree K plus 1, I would have used reduction rule 2 and deleted that, right? So in G prime, K prime, I know that the maximum degree is maximum degree is K, and there are no isolated vertices. Okay. Now I say that, okay, G prime, K prime is a kernel. How? Okay. So what can you say? Okay, or assume that G prime admits a vertex cover of size K prime. Okay, let's just say that. So this G prime. Okay. So let's assume G prime admits a vertex cover of size K prime, my new parameter. Okay. Okay. So how big G prime can be now? If there is a vertex cover of size K, I know that, okay, let's say that, okay, these are my vertex covers. I don't know, but I'm just assuming, right? So there are some at most K vertices which are covering all the edges, right? So every edge should be incident on one of this vertices, right? Okay, and all the vertices should be somewhere here. There may be some vertex which is part of some edges going to two vertices in the vertex cover, but that is fine. Okay, right. But for every vertex, the degree is bounded by K, right? So that means if this is a vertex in my vertex cover of size K, its degree is bounded by K. There can be like at most K edges here and at most K neighbors for that, right? And that is true for every vertex. So what is the maximum number of vertices or edges possible in this graph? We have K vertices which cover every edge, and by this property, I know that, okay, a set of K vertices can cover at most K times D edges. Okay, but what is D? D is K. D is my maximum degree. It is K, right? So this graph cannot have a large number of edges or vertices, right? If it admits a vertex cover of size K, right? So this is what we have just proved. So if GK is a yes instance and none of the reduction rules is applicable, then I have this. So this graph has at most K square vertices order of k square vertices and order of k square edges. Right. So what will I do is, I'll start with this original instance and I apply the reduction rule and I get G prime, right? What I have just proved that if G prime K prime is a yes instance, then it can have at most K square vertices or K square edges. Okay. So if G prime has more than if G prime has more than K square vertices, I can directly say no, right? It cannot admit a vertex cover of size K. Okay, right. What if it contains at most K square vertices? So so this is what I've done so far. So I started with this instance and I used my reduction rules 1 and 2 repeatedly, and I got G prime, K prime, my new instance. It is clear that they are equivalent instances. And what I have just proved that if G prime admits a vertex cover of size K prime, then it contains at most K prime square vertices. So if the size of G prime is greater than K square, I immediately say no. See, that cannot admit a vertex cover of size K prime, right? Otherwise, can I say yes? I don't know, right? I cannot, I'm not sure about that. But the good news is that otherwise I have the property that G prime is less than or equal to K square. So this is a size which is independent of M, right? Which is depends only on M. Okay, so and this is the kernel that I'm looking for. Okay. Yeah. So there exists other, I mean, this is the easiest kernel that you can think for vertex cover. There are other kernelization algorithms for vertex cover which give better kernels. By better kernels, I mean whose size is less than K square. Actually, there exists linear kernels. So the size of kernel, the graphs whose size depends only on K. So we'll go to the next problem. So we have proved this, that a vertex cover parameterized by size by K admits a kernelization algorithm or admits a kernel of K square vertices and K square edges. Okay, right. Okay, let's see next problem. Okay. So the next question that we will discuss is the edge clique cover problem. We'll see. I think I have 15 more minutes. We'll see how much we can. Okay. Okay. So all of you know what a clique is, right? It's a complete subgraph, or it's a okay. It's a graph on a subset of vertices such that they are every vertex is or they are pairwise adjacent, right? So like for example, this is a clique of, if you take a single vertex, it's a okay, this is not interesting in this problem, but let's see. So this is a clique of size 1, and if you take a edge, just an edge, it's a clique of size 2, and take a triangle, that's a clique of size 3, and so on, right? Okay, great. So the question is, you are given a graph G, and you want to cover all the edges using cliques. I mean, that is not a very difficult question, because if you are given a graph G, you can always take one edge separately, and we have just said that okay, every edge is a clique of size 2, right? Okay, so you can start with any graph and take one edge at a time, and that's a clique cover. But what we are interested in is covering all the edges using the minimum number of cliques as possible. right? So we want to reduce the number of cliques used to cover the graph. Right? So here, like for example, in this graph, what will be the minimum number of cliques required to cover the graph? So you have this triangle. I mean, you can take this. So let's say ABCs, right? And you can take BCD. That is also a clique, right? So the edge BC is covered twice, but we are okay with it. Okay, right. So here the minimum number of cliques required in an edge clique cover is 2. And we are trying to minimize the number of cliques. I mean, you can use any size clique as you like, but you want to try to, but you are trying to minimize the number of cliques. Okay, is the question clear? So this is again an NP complete problem. So we are trying to solve it. Okay, the parameter is the number of cliques that we are going to use in the solution. Okay, right. So the question, you are given a graph G, decide whether the edges of G can be covered using at most k cliques. Parameter is k. So what are some of the easy reduction rules that you can think of? Some easy pre-processing, trivial ones. Anybody? Okay. Remove vertices of degree less than or equal to 1. Good, right? Yeah. Right. So you can, if can you remove a vertex of degree 1? Okay, we'll come to that, right? So if a vertex is of degree 0, okay, fine. You can, I mean, that's not part of any edge, so it's not interesting to us. It's you delete. What about vertex of degree 1? So let's say V is of degree 1. V has exactly one edge. Let's say VU. How can we remove V safely? We have to do something more, right? So we have to cover this edge, VU, right? So there is only one way to cover this edge, which is by that edge itself, because it's not, V is anyway, it's not part of, it cannot be part of larger cliques, right? So you have to choose V, the edge VU. So your first reduction rule is to remove isolated vertices, vertex of degree 2. So if there is an isolated edge, okay, I mean, okay, I am doing something different. So if there is an edge which is isolated, that means it's like this, it's a connected component which is just an edge. Okay, you can delete this and you can decrease it, decrease k by 1, because you have to choose that k2 as part of your solution. And okay, so you have deleted isolated vertices and isolated edges also. Okay, now, so this one is the, I think, the non-trivial part of this. So the third one, so what you'll do is, let's say there are two vertices, U and V, and if the neighborhood are the same, this neighborhood of U and neighborhood of V, that means they have an edge between them and they have the same set of neighbors. Okay, so you have an edge from U to some W, then we say that, okay, there is an edge from V to W also, and that is true for it. So suppose such two vertices exist, that n of U and n of V are the same, then we say that we delete one of them and just keep the other. Is it, why is it safe? It is okay. Before that, is a reduction rule clear? Like for example, if you want to give an example, so let's say that you have U and V, and mean, there are same set of this and might have other edges here. Doesn't matter. So what you'll do is you delete V from it and just keep U. Okay. Do we get an equivalent instance? See, we haven't changed the budget by any, we haven't changed the budget, but so let's say that you started with graph G and then you use reduction rule 3 and you got a new G prime. So are they equivalent? Can I say that if G admits a clique cover of size K, then G prime also admits a clique cover of size K. And also if G prime admits a clique cover of size K, then G also admits a clique cover of size K. Actually, I can, right? Because, so let's take G prime, right? And consider an edge clique cover of G prime. Let's say that G prime has cliques, it's covered by clique C1 to some CK, right? And so U is in G prime, so U is covered in some cliques, right? Right. So U is here and U is here. Okay. Now, any clique U is part of in G prime, okay, in what you do in G is, so you take the same cliques. So these are the same cliques. Okay. Okay. So let's say that, okay, these are the same cliques and U is in all of this, right? So this is in G prime. Okay. So when I come back to G, I have U also. I have V also, right? So I have V here. Okay, can I just add V to all these cliques and can I say that, okay, all of them are still cliques? I can. Why? Because, okay, so let's take this. So let's take two vertices here. Let's say it's U, V, so W and X here. And I know that since it is a clique, there is an edge from U to W and U to X, right? And I know that in G, the neighborhood of U and V are the same. Therefore, I have an edge from V to W here and V to X here also. And it is true for any WX in that clique. Okay. So if I can cover G prime using K cliques, I can cover all the edges in G also using K cliques if I add V back to it. Okay. Right. So that was the intuition, or that was the proof that they are equivalent, or it's this reduction rule. It's safe to use this reduction rule. We'll still get a equivalent instance. Okay, right. Now let's use these three reduction rules, and it's easy to see that they all of them take only polynomial time also, right? So you use this reduction rule exhaustively, all these three reduction rules exhaustively till it cannot be used. Okay, and let's say that we get a new instance. So G, okay, and you get G prime. Okay. One of the presented P prime, then V prime is for a S instance. We should have written this. Okay. Okay, I get this G prime. So what I'm claiming is G prime is a kernel. G prime is a kernel of size at most 2 power k, right? And yeah, so in other words, what I'm saying is, okay, if G prime has more than 2 power k vertices, then I can safely say no, it's a no instance, right? Okay, so why should this be true? Why should G? Okay, so what you have to prove is if G prime contains edge clique cover of k cliques, or every edge of G prime can be covered using k cliques, then G prime contains at most 2 power k vertices. How can we prove it? I think I can give you like 2 minutes to think. So assume there exists, okay? So let's say G prime admits edge clique cover of K cliques. Okay, so that means you have G prime and there are like some K cliques which is covering every edge, right? So every edge is part of some K clique. So, and yeah, every edge is part of at most K cliques. So let's call these cliques C1 to some CK, right? What you want to prove is there are at most 2 power K vertices. Why is this true? Okay, so to prove this, let's take every vertex. So let's say vertex V1 to, let's say. Okay. Now for every vertex, we'll make something like a chart. Okay, right. So let's say this, so there are C1 to CK cliques, right? If V1 is covered by C1, I'll put a 1 here. Okay, now I go to the second clique. If V1 is covered in C2, then I put a 0 here, and so on. Okay, like this I will do for every vertex. So for every vertex, I'll assign a string to every vertex, a K length string, and it's simple, right? So if a vertex is contained in the ith clique in the solution, I'll put a 1 there, otherwise I'll put a 0 there. Okay, so for every vertex, I have this. Now let's say that okay, V1 has a clique, has a string attached to it which reads something like 101001. Let's go to another vertex. Let's say V2. What I'm claiming is that V2 also cannot have the same string as V1. That is, V2 also cannot be part of the same cliques as V1, the exact same set of cliques as V1. Okay, so why is that claim right? What happens if they are part of the same cliques? What if they are part of the same cliques? So you have V1. So V1 is this part of some clique. So that means it is adjacent to all these vertices in C1. And there is some other clique and V1 is adjacent to all those vertices also. And I'm saying, okay, V2 is also in this clique. That means V2 is part of that. It's adjacent to all the vertices. Yes. And V2 is again this. Right. Yeah. So if V1 and V2, if the corresponding bit string is the same, then that implies that neighborhood of V1 and neighborhood of V2 are the same. Then we would have used reduction rule. Yeah, we would have used reduction rule 3, right? But our assumption is that none of the reduction rules can be used on G prime. Right? Okay. So therefore, we can say that, okay, this is not possible. That means for every vertex, you have a different bit string attached to it. So if you look at V1 and you look at its row in the chart with respect to the cliques, now you take any other vertex and look at the row as corresponding to it, you get they are going to be different, right? So every vertex corresponds to a different string of length K. But how many bit strings can be there of length K? There can be at most, there are like K bits, everything can be 1 or 0. There can be at most 2 power K strings, right? That means there can be at most 2 power K vertices in the graph if it is a yes instance. So if you get after the reductions, you get an instance which is of size greater than 2 power K, you can say no. Otherwise, you have an instance which is of size at most 2 power K, which is a kernel by definition. Okay, so that's what. So edge clicker admits a vertex kernel of size 2 power k. That's what we have proved. Okay. Again, these are, I think, the easiest example that you can see in kernelization. There are other much sophisticated techniques used for designing kernels. But so the third technique, I don't think we have time for it, so we'll skip it. So also thought we'll cover iterative compression, but let skip that. There are any questions? So in iterative compression, the basic idea is this. So you start with, okay, so you have an instance, okay, and let's say you are looking for an instant, a solution of size k, right? So you're looking for a solution of size k. This is the question that you're looking for. And let's say that somebody has given you, or some, you have got a solution which is not k, but slightly larger than k, right? Let's say that, like for example, in vertex cover, you're looking for a vertex cover size k. You don't know how to get that. That is difficult to get. But yesterday you have seen how to get a solution of size at most 2 times opt, right? Using an approximation. So in polynomial time, you say that, okay, you get a solution of size 2k, right? Okay. Now you haven't answered your question. You have just said, okay, there is a solution of size 2k. Okay. Okay, it might not look very structured like this. So let's say you have, okay, you are looking for a solution of size k, which you don't know. But what you have is a solution of size 2k, okay, which might look like this, right? This you can find in polynomial time. Okay, right. So suppose you have this solution. In iterative compression, what you do is you try to compress this larger solution to a solution of size that you need. Is a solution of size k, right? And okay, the standard technique that you use is, okay, so you have this which is bounded by k. You guess this part, right? How this larger solution will intersect with the solution that you are looking for, right? So this you can do in NFPT time, and after this you will try to find this part, and this can be done in FPT time. For at least for vertex cover, though, you can do it very easily. Okay, yeah. So I don't know how much justice I did to this, but this is the overall idea. I can give you I can point you to references later.
Yeah, if there are any questions, we can continue discussion through our Zulip. I hope all of you enjoyed the talk. It was a nice talk. Thank you, Dr. Pradeesh Ashok, for giving the interesting talk. And participants, we can continue approximation algorithm at 2:30 p.m. The talk is given by Professor Muralidhara. See you at that time. Thank you all.